This is very important lemma. If f is absolutely continuous on closed interval ab and f dash x equal to 0 almost everywhere, a dot e dot means almost everywhere, then f is constant. We need to show that f is constant. Now for this proof there is a little explanation. A function f is absolutely continuous on closed interval ab if and only if it satisfies the fundamental theorem of calculus. That is, for Lebesgue integration, it can be represented as the indefinite integral of its derivative. That is, fx can be represented as f of a plus the integration of f dash t from a to x for all x belonging to the closed interval ab. Now what is given to us? Now f dash x equal to 0 almost everywhere on the interval, right? So the integral of the derivative evaluates to 0, right? So this equation will be changed into f of x equal to f of a. That's it, right? Now f of a is the fixed value, which means what? F of x is then constant. This is what is needed to be shown. So fx must be a constant function. So this is what we are going to do in the proof. So let's start with the proof. Now suppose this is your interval, the closed interval from a to b, right? And f is absolutely continuous on this interval. Let me take a point C in this interval. The point C can be any point. Over here, over here, over here. It can be any point. So we are taking any point C that belongs to the closed interval AB. So for this point, any point C belonging to this interval, or we can say that for all C belonging to the closed interval AB, f of A is equal to f of C. Here we have shown that f of A is equal to f of x for all x belonging to the closed interval AB. F of A is equal to f of x for all x belonging to closed interval AB. So here f of A is equal to f of C for all C belonging to the closed interval AB. Here x is replaced with C, right? So we have taken the point C belonging to the closed interval AB, for which we have to show that f of A is equal to f of C. And because f of A is your fixed value, the value of the function at this endpoint, and that is equal to f of C. C is any C belonging to the closed interval AB. So we say that f is constant. Okay. So for this, yes, we need to show that f of A is equal to f of C for all C belonging to the closed interval AB. Right? Okay. Let me consider the set E, which is the subset of the open interval AC. E is a set which is a subset of the open interval AC. We are not taking the endpoints A and C, right? It is the open interval. And this set E is of measure C minus A. Right? It is a subset of the open interval AC, so we are taking the measure of E to be C minus A, the difference of these 2 points, to which E is the subset, in which it is given that f dash x is equal to 0 in this set E, right? So let's write this. Let E is a subset of the open interval AC with a set of measure C minus A, in which f dash x is equal to 0, right? And let's consider the epsilon and eta be the arbitrary positive numbers. Now to each x belonging to E, to every x in E, there is an arbitrary small interval. Let me take this distance to be h. And this point becomes x plus h. So for each x we are having this small arbitrary interval, the closed interval x plus h, right? And this interval is contained in the open interval AC. Alright, we can also say that in the closed interval AC. It may also be contained in the closed interval AC, such that the mod of f of x plus h minus f of x divided by the difference of these 2 points, that is h, should be less than, instead of epsilon I'm writing eta over here, it is also as small as that epsilon, a very small positive number, same as that of epsilon. I'm taking this eta. So let me write this first. To each x belonging to the set E, there is an arbitrarily small interval x plus h, right, contained in the closed interval AC or open interval AC. I'm writing here the closed interval AC, such that the mod of f of x plus h minus f of x divided by h is strictly less than eta. What is this representing inside the modulus? It is the average rate of change over the interval. And this condition implies that near x, the absolute value, this is the absolute value. Near x, the absolute value, near x, the absolute value of rate of change is bounded by, it is bounded by eta, which is as small as the positive epsilon, right? And this is the form of, you can say, and this is just the form of the local Lipschitz condition. So we have applied that over here. It is the form of Lipschitz condition. So further it can be written as mod of f of x plus h minus f of x strictly less than eta into h, and marking this as 1. Therefore, now by Vitali's lemma, we can find the finite collection of the intervals xk, yk. We can find the finite collection of these intervals, the non-overlapping intervals. Non-overlapping intervals means they are not sharing the common points, right? So we can find the finite collection of these non-overlapping intervals of this sort which cover all of E. That covers all of E except the set of measure less than delta. Except the set of measure less than delta, it is covering all E, right? So by Vitali's lemma, we are saying that we can find a collection of the non-overlapping intervals of this sort which cover all of E except for a set of measure strictly less than delta. This is the delta which is defined in the definition of absolute continuity. It is that delta which is defined in the definition of absolute continuity, right? So where delta is the positive number corresponding to epsilon, that is why I have mentioned there eta, because here I have mentioned eta instead of epsilon, because I am going to use this epsilon with this delta for the definition. So it is in the definition of the absolute continuity of f. Now let's label this yk as, if we label yk so that yk is less than equal to xk plus 1, what do we have? if I take k to be equal to 0, I will be getting y0 less than equal to x1, and y0 or y0 is our starting point A, right? So let's give the sort of these intervals. It is A equal to y0, which is less than equal to x1, and x1 is strictly less than y1 because our interval is of the format xk yk. So naturally, if I put k equal to 1 x1 and it is y1, so here x1 is less than y1. So x1 is strictly less than y1. For k equal to 1, we get y1 to be less than equal to x2. So y1 is less than equal to x2. Then again x2 is strictly less than y2, and y2 will be less than equal to x3, up to so on, less than equal to yn, which is less than equal to xn plus 1, and we have taken this xn plus 1 to be equal to the last point C, for the interval AC, where the set E is present. For this interval, we have taken y0 to be equal to A and xn plus 1 or yn to be equal to C, the endpoints of the interval, right? Okay. And that is the summation on xk plus 1 minus yk. xk plus 1 minus yk. And the summation is from k going from 0 to n. This is strictly less than delta, right? So therefore, by the definition of, because f is absolutely continuous, so by the definition of absolute continuity of f, we have, okay, by the definition we have, therefore the summation on mod of f of xk plus 1 minus f of yk to be strictly less than epsilon, and the summation is from k going from 0 to n. Right, very fine. Okay, now I am interested. Okay, this definition is for the inequality, this one, right? Yk less than equal to xk plus 1. I am interested to define this on this interval where xk is less than equal to yk. I am going to define on this. Now taking the left hand side as it is for that interval. Now let me consider the summation on f of yk minus f of xk, right, for the interval xk yk. Let's check what is this strictly less than. K is from 0 to n. Now what is mod of f of yk minus f of xk? In the very start of the proof, we have marked here the condition 1. F of x plus h minus f of x mod is strictly less than eta into the difference of these 2 points, that is h. So from here we say that, so this is less than equal to the summation eta into the difference of these 2 points, that is yk minus xk, using 1, right? Okay, if I take this eta outside, we are getting the summation on yk minus xk. Now what is the summation of yk minus xk? The sum of the differences of the non-overlapping intervals xk, yk, which are covering the set E having the measure c minus a. Yes? So the sum of such kinds of intervals that are covering the set E, that sum should be strictly less than c minus a, because E is a set of measure c minus a, the length. So their sum is strictly less than c minus a, right? So we are getting the summation on this mod to be strictly less than eta into c minus a, by the way the intervals were constructed. Please mark this as 2. Now finally we are going to find the mod of f of c minus f of a. I need this value to be equal to 0, right? Let's check this. Okay, what is mod of f of c minus f of a? It is the summation on f of xk plus 1 minus f of xk and the mod. When you sum up this, you will be getting back your fc minus fa. And the sum is starting from k going from 0 to n. So this is further equal to the summation k going from 0 to n. I would like to add and subtract f of yk plus the summation on f of yk minus f of xk. I have just added and subtracted the summation on f of yk into this mod, right? So adding and subtracting summation of f of yk. Further, this mod will be less than equal to, let's separate them. Now this will be less than, strictly less than epsilon by the definition of absolute continuity. Yes. So we have written this to be strictly less than epsilon plus, what is this mod? Summation on this mod? We have just found that the summation on this mod is strictly less than eta into c minus a. So this is eta into c minus a. Now since epsilon and eta are arbitrary positive number, I can take this to be as small as I can, right? 0.0001, as small as I can, any positive number. So this right hand side may approaches to 0, means it is approaching, it is tending to 0, right? So which means if mod of f of c minus f of a is strictly less than epsilon plus eta c minus a, where since epsilon and eta are two arbitrary positive numbers, so what we are having inside the mod, that value is equal to 0 because this will be tending to 0. So from this we get f of c to be equal to f of a for all c belonging to the closed interval ac. And because this f of a is your fixed value, so therefore f of c is constant for all c belonging to closed interval ab, that is f is constant almost everywhere, right? So here ends up the proof. It is a very beautiful proof, right? Okay, please revise this again and again. Okay, thank you, stay blessed.